The James Webb Space Telescope recently pointed its mirrors at a planetary nebula known as TC-1. What it found was a spherical shell of material spanning light-years across, perfectly surrounding the dead remnant of a white dwarf star. But the strange part is the composition of that shell. It is made entirely of microscopic molecules called fullerenes, hollow spheres constructed from exactly 60 carbon atoms, commonly known as Buckyballs. Because this nebula takes the shape of a massive geometric cage, it looks suspiciously like a theoretical megastructure. It raises the question of whether this is a light-year-wide Dyson sphere constructed to encapsulate planets. On Earth, these exact same buckyball molecules are highly efficient materials for advanced energy capture. We use them in solar panels to absorb energy and move electrons efficiently along a circuit. It is worth investigating whether we found an alien power station beaming energy to trapped worlds, or an incredibly rare, perfectly natural astronomical event. Testing the solid casing aspect of a Dyson sphere requires looking at the actual spatial data. This diagram compares two density models. While tempting to picture a thick carbon fiber dome, infrared data shows the buckyballs are actually a diffuse gas. Even though the cloud forms a sphere, the individual molecules are separated by millions of miles of empty vacuum. This lack of physical connection challenges the theory of endohedral encapsulation. In chemistry, this involves trapping a single tiny atom inside the 1 nanometer cage of a single buckyball. Scaling to a planetary level, any world inside TC-1 would float through a thin, sweeping fog, made of quadrillions of microscopic cages, rather than being contained by one massive shell. This structural reality complicates the fractal universe theory, the idea that cosmic structures are just larger versions of the molecules seen under a microscope. While the nebula mimics the shape of a molecule, it lacks the chemical bonds. The shell is held in place by gravity and radiation pressure, whereas a true molecule relies on electromagnetism to stay together. If the physical structure isn't an engineered shell, we have to look at the thermodynamic system. Could the chemistry of this gas still function as an active energy beam? In material science, C60 is one of the most effective electron acceptors known to exist. It readily captures electrons generated by light, making it an essential component in organic photovoltaics. In their pure form, buckyballs function as highly capable semiconductors. When doped with elements like potassium, these molecules can conduct electricity with zero resistance as superconductors. The energy source driving the system is the central white dwarf. This incredibly hot remnant floods the nebula with lethal ultraviolet radiation and high-energy particles. The fullerene shell intercepts that intense output. The carbon bonds absorb the incoming UV hits without breaking down, creating a resilient radiation shield. This schematic tracks that energetic conversion. The buckyballs process the high-frequency ultraviolet radiation, absorb the energy, and re-emit it as long, smooth waves of safe infrared heat. That secondary infrared glow is exactly what the James Webb Space Telescope picked up to detect the shell in the first place. The entire nebula operates as a massive passive cosmic radiator, processing the raw stellar radiation into a stable thermal environment. TC-1 is a naturally occurring event, the scattered remnants of a supernova explosion that formed a geometric shell of carbon as the system cooled. Any planet surviving inside this nebula is protected by a light-years-wide fullerene shield, constantly bathed in a safe, warm infrared glow from the sky above. This astrophysical reality is a testament to a fundamental law of scale. The universe naturally constructs cosmic scale phenomena using the exact same optimal geometric shapes that humans engineer for our most advanced technology. Nature repeats its most efficient blueprints across every scale, from the geometry of a single carbon molecule to the structure of a light-year-wide nebula.